Okay, so in the lab we are building diode lasers, and so let's discuss diode lasers. The questions that we want to address right now is that first of all, if you recall, I was drawing a figure which looked like there's this question of here's your frequency, here's the gain bandwidth, right? And I always draw them not looking the best, but gain bandwidths can look pretty ugly. All right, they're just white. That's the only thing. All right, and then we were able to by decreasing L, we have just the one mode, right? But that's misleading to draw it like that, because as I discussed earlier, there's a certain let me show the other. So maybe there's another mode here, and this is delta nu, right, the cavity mode. But then this mode that's permitted has a certain width to it, right? And so this is delta nu L, right? And what we will find is that in the case for commercial diode lasers, okay, this delta nu L is on the order of so first of all, what's delta nu G? Okay, so actually I'd like to talk about delta nu G first. Delta nu G, how to estimate that? Well, it turns out, so I mean, I know the wavelength bandwidth, so this is on the order of 50 to 60 nanometers. Okay, so that's the bandwidth. Well, how to get that in terms of hertz and all that? So what you can remind yourself is that sunlight, okay, the visible, that goes from about 400 nanometers, which is blue, out to 700 nanometers, which is way into the red, almost infrared. So that's 300 nanometers, and this, if I remember, so 300 nanometers, and in one of the slides earlier we had said that this corresponds to a delta nu G, and I'm sorry I keep making them uppercase or lowercase as G, but this was something like 5 times 10 to the 14 hertz, okay, and so that's 300, and so 60 nanometers is about a fifth of that. So I'm going to estimate from here that this is about 10 to the 14 hertz. Okay, commercial diode lasers. That's the gain profile. Okay, and the delta nu L tends to be on the order of, so this is the laser that you've been using so far. It's anywhere from about 100 megahertz out to gigahertz. Okay, even 10 gigahertz. It can even be 10 gigahertz. So something like that. Okay, and actually you did measure your coherence lengths, and from that we had estimated a certain bandwidth. I'd have to go and look back at those. Sometimes you can even have smaller bandwidths, but 100, let's say 10 megahertz to a gigahertz would cover it completely. Okay, but you remember that for experiments that we were planning, in fact in general for experiments in quantum optics and quantum information and atomic spectroscopy for research experiments. The scale is set by the natural line width, right, and it's 6 megahertz for rubidium. Okay, so what we will do in our lab, okay, we will build an ultra narrow bandwidth ultra frequency. So not only will it be narrow bandwidth, but the frequency of that mode that we will have, it will be tunable. And not only will it be tunable, it will also be ultra frequency stable. So this line will be very narrow, and you can tune it over a large distance controllably, and also wherever you tune it to, it will be very stable right there. So ultra frequency stable. So it's the ultimate laser, okay? So diode laser system, that's what we're building. Okay, that's what we'll do. Now, what we mean by ultra narrow bandwidth is that your laser line width is going to be this diode laser system. The laser line width is going to be on the order of 1 to 10 kilohertz. Okay, and it will be tunable over a wide enough range that you will be able to see all the different values that the spin of the nucleus can have. Okay, so I'll just write that: frequency tunable and stable enough to reveal all the different quantum values the nuclear spin can have, the rubidium nuclear spin can have. So it's quite the ultimate diode laser system that you'll make. Okay, so that's one thing that we will do. And this, when we start to, so in the end, your diode laser line width is going to be, you're going to narrow it, okay, and it's going to look something like this. Okay, so I'm just going to write this in here, that this is going to be delta nu L after frequency narrowing, and that's something that you will do in the lab using an ingenious technique for which people, the Nobel Prize winners in 1997, got the Nobel. This was one of the reasons. Okay, they invented this method. So in the context of diode lasers, we're going to study how to narrow the bandwidth of delta nu sub L. That's one thing. The other thing that you will notice is that when Kifan's making a video on how to set up this diode laser and how to narrow the bandwidth and everything, the other thing that you will notice is that when the diode laser is fired up, when the diode laser is fired up, meaning turned on, the spatial profile is there's two things. It's highly elliptical. Okay, so the beam would look something like, for example, if I were to draw it, it could have any orientation, but it would be, so let me just draw the ellipse like this. Okay, it might look like this, or it might look like that, or it might look any orientation. Okay, but it's highly elliptical. The other thing is that it's easy to verify that the polarization of the laser output is aligned with the short axis. Of the ellipse. Okay, so these are things that we would notice. So this is sort of interesting. And the highly elliptical, well, and so what it means is that if the ellipse, if the beam coming out from the laser diode, the ellipse looks like this, it's horizontal, then the laser polarization will be like that. If it's like this, then the laser polarization will be all like this. In this case, it will be like that. Okay, and so the question that arises is, of course, why is this the case? Why? Okay, and so that's what. So these are now lab-related questions, and so we will discuss this in the next video, that why is the beam profile elliptical, and why is the polarization always orthogonal to the long axis and aligned with the short axis. Alright, so that's in the next video.